And thanks everybody for joining us for Construction Tech today. We have Daniel Kress of the Smart Plus Academy. We're really looking forward to this presentation today. The Passive House Accelerator is a collaborative online platform for sharing innovation and thought leadership in passive house design and construction. We publish articles and interviews, produce weekly virtual confabs with passive house pioneers from around the world, and elevate the work and programming of the passive house movement's leaders, practitioners, and organizations through interviews, articles, social media campaigns, video, and podcasts. Our aim is to catalyze zero carbon building by accelerating the adoption of passive house building. With our hosts, co-hosts Kevin Brennan, Shannon Pendleton, Sean St. Amour, and Mark Willey, we produce Construction Tech Tuesday to share the technical, the technique, and the technology of passive house construction tech. Each week, we welcome guest practitioners to dive into the details of practice with the builder and tradesperson as our target audience. We welcome folks from all corners of the construction and design world to join us each week, and we're happy you are with us today. Thanks.
I'm Kevin Brennan. I'm from New York City. I own and operate Brennan Insulation and Airtightness, and I am proud to introduce Daniel Kress, who's a fellow tradesperson, trainer, and passive house enthusiast, spreading the message of passive house. The session you're going to see tonight is going to be about cooling in passive house and all the technical details and the calculations that come into it and how it can be done. Daniel's focus is great, and I wish you guys hold on to your seats. You're gonna be blown away.
Thanks, Kevin. I'm Shannon Pendleton. I'm a designer and passive house consultant at Sanderson Design, and I'm zooming in tonight from the East Coast in New Hope, Pennsylvania. And I'm looking forward to tonight's presentation as well. How about you, Mark?
Well, it's great to have some of our recent presenters on. Our 25th episode was with Reed Rollins, our 26th, who was with Steve Hessler. And we really enjoy the questions that come up from the audience throughout. And so a reminder to everyone to put a Q with the question. And tonight you'll be hearing some terms that might be foreign to you. So please go ahead and say, what does Kelvin mean? Please go ahead and say, what's a delta T? What is metric, right? Whatever your question might be, what is the square foot you speak of? So whatever level your question is, bring it forward. And I'm thrilled to have Daniel here tonight. And I pass the mic to someone who's in the field, Mr. Sean St. Amour.
Good evening, everybody. Hopefully you guys can see me and hear me okay. I'm in Squamish, BC. You can see the mountains in behind me. I was just working with Ryan and his team on a job site here. They're just getting started, trying to figure out the whole air barrier system, going through the details. So live from a job site here in Squamish, BC, going through the details, and great to see Daniel. I feel like we're a day ahead of us. It is Tuesday here in Vancouver, but really it's Wednesday because we're going to turn it over to Daniel. Daniel, fire up your engine. Let's get the show started.
Yeah, thank you. Hello, everybody, and thank you for having me. And you're right, Sean. Australia, we are always ahead of you guys. Time-wise. Yes. I'm really excited about speaking to you today. I spent lots of time on translating because it's now multilingual. It's speaking about metric and speaking imperial, like what I call normally body part calculation, because you're using feet, you're using body temperatures for your measurements. So I call it body part calculation. So yes, so today we speak about cooling in passive houses. And the spread of depths is really, really wide in my presentation. It is for everyone, something in there for people that are really deep in it and mechanical engineers, but as well for somebody that just started and want to get the whole idea of passive house from a cooling perspective. To some extent, I'm going from macro to micro and then going out to macro again. So it's like from the big picture to the small picture and like going into details and then coming out of the details again to find actually the solutions. Yeah, so that's pretty much the flow of this presentation. Let me reset my timer that I know where I'm at. Okay, so let me first introduce myself. So I'm Daniel Kress, and a fun fact about myself is that I avoided passive house for the first 10 years of my career. I didn't want to rely on a ventilator to get fresh air in my home, and that's what was completely against my beliefs. I was really a naturalist. So I started my career as a carpenter back in Germany, building eco homes. And then I moved to Ireland and really quickly realized an eco does not mean sustainable. So I started to dive deep into the sustainable, like I was looking for sustainable building solutions. Then after I understood that sustainable is not actually really healthy, then I dived deep into the passive house world. And now 3 university degrees later, 2 in Germany, 1 in Canada, I actually know that passive house is the foundation for healthy and sustainable buildings that are affordable. That's the foundation for affordable buildings and living that is healthy and sustainable. Then after my university, I actually went to do a EU project in knowledge transfer between different universities and countries. And I was focusing on the different national building standards and compared them to the passive house standard. The conclusion was really clear. Passive house provides the best results, the closest results to reality. We had discrepancies of up to 700% between reality and the standards. So that's when you're putting lobby factors in there and political factors into the standards. You can't use it for economical assessment. So the result was at the end, passive house is the foundation for healthy buildings that are affordable. And passive house is nothing special. Passive house is not a breakthrough in science. It's just going back to the roots. Passive house is just implementing the laws of physics and economics to make our decisions. Then I moved to Australia. I started to build high-performing buildings in 2015 in Australia. I founded Smart Plus in 2017 from smart buildings that are plus positive, Smart Plus homes. That's where we started. And then I transformed into a Smart Plus Academy because I realized we need to educate for more and I need to share my knowledge. And that's exactly what we're doing now in Smart Plus Academy. We already taught hundreds of people and supported hundreds of different companies out there. And our pass rate in our exams is at 99%. Our global average is above 25% in the exam attempts, like from the points that people get. In the last 6 months, we had 100% pass rate. And of the last 198, of the last 198 people passed. So the way that we teach and the way to this success is by having a certification package that is actually the pre-course. We call that Palama, Passive House Language and Mathematics. Then the Certified Passive House course with replay finally. And now the exam prep and then the exam, and this package together is making that possible. Exactly the same we're having for, we're having the replay, exactly the same we're having for the tradies, exactly the same structure, just everything is a little bit shorter. So the Palama is something that can be actually done on our website. It's a self-paced and it's existing for the tradies as a half-a-day session and for the designers as a full-a-day session, and it is self-paced. Okay, so where could you find that on the website? Just go to the website, go to our courses, and then these nice 3 colors are coming up. Green is designers, blue is tradie, and orange is the community. And you find in here now the Palama courses in that list, and that's where you can find the courses. But that was now enough about me and what we actually do and where I'm come from. But I hope that gives you an understanding where I come from and why you may want to listen to me. So I would like all of you go to your phone and put it on silence and put the screen down and close all your other like browsers, only having Zoom open, because what I'm telling you now and what I'm speaking about now took me years to understand, and I give you that now in less than a half an hour. So you could spend on your own studying that for another few years, or you have now a half an hour and you get that. So please put your phones on silence, put the screen down, and close your other browsers and focus on that. It's important. And I spent days of actually putting that together for you, especially now translating it all into the American units. So what's the learning objective? First of all, I want you to understand why cooling is not an issue, and that it is far easier than that hot climate is far easier. I want to explain you why cooling is cheap and heating is expensive. And then I want to give you the understanding of the limitation of heat recovery ventilation systems for cooling. And then why we actually want to use air as our conditioning medium and not like a water or something else that has a far higher energy density. So you probably realized already I'm going through my slides pretty quickly, and you will get a little bit of information overload, and it may feel a little bit like this little girl here drinking from a fire hose. Yeah. Stay tuned. We will get through that, but you will see you're able to follow the logic and what I'm presenting to you. So the content is first cooling versus heating, then why cooling is cheap, then the availability, the available capacity of cooling via air. And that's the technical part, that's the micro approach, and then cooling systems design and how to approach it all. So let us start now. Is it possible to build a passive house in hot climate? Yeah, is it possible, guys? Yes, it is. Heat does not know what's the difference between inside and outside, guys. There is like, they don't know it. Yeah, so in a hot climate, we're having our energy coming in from the outside to the inside. Yeah, so if we are in Darwin, or what's really hot in US, probably Mexico, New Mexico, or Texas. Yeah, there the heat comes in from the outside. And it doesn't matter if you're in Darwin or if you're in Alaska in the hot time, the heat comes in from the outside, and we're designing for that climate where you're building in. Then cold side, yeah, if you're building now in Hobart in Australia, or you're building in Toronto, yeah, now in the winter time, we're designing for that coolest day of the year and making sure that the maximum load per square meter, so 10 watts per square meter would be more or less 100 watts per square foot. Translating into BTM, it's 3.2 BTM per square meter, a square foot, something like that. I think that's your unit. So here it just leaves the building. Yeah, it's an energy flow through a build-up. We do the heat doesn't know if it goes from the inside to the outside or from the outside to the inside. That's the first really important thing that we want to understand. Then the thermal difference. Yeah, we want to speak about thermal difference. We could have the situation that like the outcome of passive house is always the same: a healthy and sustainable building, like a healthy and comfortable indoor environment between 20 and 25 degrees. And underneath you see now the translation already. And now we could have on the hot side, high extremes 45 degrees, a thermal difference of 20 Kelvin, or on the cold side 0 degrees, a thermal difference of 20 Kelvin. And you see now the thermal difference on the low side and on the hot side is exactly the same, because from 25 to 45 it's 20, and from 0 to 20 it's 20 as well. So the thermal difference is the same. So that's in a mild climate, yeah, or like in a stable climate. So your thermal insulation performs in the winter as in the summer. When we're coming now to a cold climate, taking here the example from Freiburg, where I'm from in Germany, hot climate in the hot temperatures goes up to 40 degrees. In the cold season, it goes down to minus 20 degrees. So now we see on the cold side, we have a thermal difference of 40 Kelvin, and the hot side, we have a thermal difference of 15 Kelvin. And we see here already that we need to design for the cold climate. Yeah, and here we have a thermal difference of 40 Kelvin. When we're now looking to hot situations, normally we don't have really areas where we live where the temperature goes above the 50 degrees Celsius, yeah, or 122 Fahrenheit. Anybody living in temperatures where you're reaching 50 and more? Probably not. But this is normally like a really extreme high temperature, and then maybe the temperature only drops down to 10 degrees. But when we look now to the cold season, -20 is nothing special. We have -35 in Toronto. We have -40 in Siberia. So -20 is nothing special, but we see already we are able to build in that areas for decades already. Yeah, and the thermal difference is 40 Kelvin. In the hot climate, the maximum we normally get is about 25 Kelvin. We can handle that. It's easy. Yeah, the difference is smaller. Yeah, so we need even a thinner wall for this type of climate. So hot climates is easy. So is overheating an issue in passive house? Here I want to come from a little bit an intellectual point of view and a future look, like I'm looking into the future. Imagining that we're having a future that is purely based on renewable energies. Yeah, and that's where I'm going now. So here, reducing cooling energy. Cooling is only needed when the sun is shining. There is no other reason why it is getting hot. If the sun would be off for just 7 days, all our oceans would be frozen. Yeah, the surface, not the whole way through, but the surfaces would be frozen. You could be ice skating around the whole world. 7 days the sun is off. The only reason why it is hot is the sun is shining. When the sun is shining, the PV system, the solar electrical system on the roof is able to produce energy and is be able to use for cooling. And the investment cost is normally about 2 cents per kilowatt hour. So our homes can become the power stations of the futures. And we need to really think about produce, store, and distribute from our houses. So I believe that our houses will be plus energy houses, the power stations of our nations, gives as well the power back to the people, because now we don't have these big corporates that are actually supplying energy. It's the little house owner that is able to actually have a piece of the cake on the income of energy production. If you're looking now what is possible, England produces 4 times the required, or can produce 4 times the energy that it's needed on the surfaces facing the sun with already 15 to 20-year-old technology. Yeah, England, where the sun never shines. Yeah, so it's easy, especially in areas like Australia and most parts of America. When we look to production, we have diesel production for 10 cents, coal production 6 cents, combined gas 5 cents, wind 3 cents, and solar 2 cents. So renewable energy are already winning the price battle when we're looking to the production side of energy. The problem is the storage. We need to be able to produce and store renewable energies to the price of fossil fuel, and then fossil fuel has no chance any longer because it will be replaced by renewable energies because it's cheaper. Yeah, energy production, it's already far cheaper. Let us look into storage. What type of storage is existing? We have chemical storage, thermal storage, and mechanical storage. And when we look to the pricing and the costing of storage, flywheels, 45 cents, flow battery, 28, lithium batteries, 25 cents, pumped hydro, 17 cents. The tipping point would be 3 cents. So they're coming to the 5 cents of natural gas. Yeah. So that's the tipping point. Is there a solution? Yes, there is. Invented by Ideal Lab, the energy vault invented by pretty much Bill Gross. He's the one behind that company. And he's using building cranes. Why did we not come up with that? Yeah, he's using building cranes for storage. First one is actually built in Lucerne. Just Google Energy Vault, Google Bill Gross, and you see how that technology works and how that all comes together. And you probably will see that slides again. Yeah, storage is now possible for 3.5 cents already. So we have the 0.5 cents as a green premium in the moment. And I believe soon we build that in bigger quantities. We are able to bring it down to 3. He has already pre-orders of about 20 billion or so. So storing energy, this is only 3.5 cents in the short-term storage, not in the long-term storage. What do I mean by that? Yeah, so we are having our renewable sources. We have our primary energy production. That's what we're teaching in Passive House. And now we're having short-term, we're having here our energy production, and that's our final energy. But when the energy is produced, not necessarily the energy is needed. Yeah, so we're having now our mechanical storage, the crane that I just described for short-term storage on a day-to-day basis. And we probably need chemical storage for long-term storage by going hydro, like splitting water into hydrogen and oxygen, and then using a method of power to gas, where we're going then for methane creation, like artificial methane, not from cows or not by not by natural gas. So that's the way that we have it. And we have the storage technology for all that already existing. And because of these massive losses, like we have only efficiency of about 30%, heating will always be at least 5 times more expensive than cooling. So we need to design for the cool season, despite where we're at, where we're building, except the temperature is not dropping below our 20 degrees, that's your 66 Fahrenheit. So short cost of storage, short-term storage, production 2 cents, conversion 0.2 cents, storage is 3.5 cents, comes to 5.7 cents pretty much in the moment. Long-term storage, production 2 cents, conversion is 8 cents, because if you're having 20% efficiency, that's what I put in there with the storage losses. Then storing technology, 25 cents. I'm really optimistic here. We're coming now to a total cost of 35 cents. So production is 35 cents. Production is 5.7 cents, short-term storage, long-term storage. That's the reason we have a factor of at least 6, I think, for heating costs. Heating is our parameter that we really need to control, because it is expensive. So minimizing heating energy. Heating occurs when there is a lack of energy available, the sun is not shining, it's an additional consumption during the worst time. Yeah, the heating cost will be between 5 to 50 times more than the cooling cost, depending on where you are in the world. Yeah, so even in climates like Sydney, we still design for the cold season, because the cold season will cost us more than the hot season. The hot season, from an operational point of view, costs us nothing. The investment cost upfront is probably about 2 cents per kilowatt hour. So we cannot solve our problems with the same thinking we used when we created them. So I want to a little bit discuss the professional blindness. Professionals, yeah, like surgeons, their solution is cutting. That's what they learned. Herbalists, it's herbs. Yeah, bricklayers, it's bricks. Carpenters, it's timbers. Mechanical engineers, it's mechanical systems. And obviously we can solve everything with mechanical systems when it's about energy, and they can solve it, but we probably want to go down to the passive house designer and reduce the energy consumption. But only if you all work together, we come to the best solutions. Nobody can know everything. I don't know everything. I'm really good in seeing bigger pictures and putting things together. So I have a really good understanding of a lot of things, but soon I go into the nitty-gritty. I have to speak to professionals and experts in their fields. So to understand our systems, we need to understand the parameters that we have and understand the risk parameters. So the passive house parameters we need for heating and cooling is our ventilation, our conditioning, and now the capacity of our cooling is this formula. And that creates our maximum load. That's the size of our system. V is the volume, yeah, of air that we have available as our medium for cooling. Then CP is the capacity of air, that's thermal mass of air, translated in Riemann terms. FT is just a correction factor. Delta T is the thermal difference in your location related to your treated floor area. So that's the conditioned space, and that's the formula for the maximum load that we can deliver to our passive house. So let us look at the first thing, ventilation. So when we speak about passive house teaching, we're having here our supply air with 30 cubic meters per person that we need as fresh air for every person. And we normally say in passive house, 30 square meter of treated floor area per person is what we want. Here you see now these black boxes, they are the translations. Yeah, that's now the translations part. Yeah, when you're not understanding what's up here, this part explains you what I'm talking about, okay? So here we're having 1 cubic meter of air per square meter an hour. Yeah, in other words, we have here, what would that be? About 30 square, like I'm not translating that now. It goes a bit too far doing that on the floor. And then, so this is from the supply air minimum, and that's the minimum from the minimum air supply that we have to have. We have to have at least an air exchange from inside to outside of 0.3 by passive house teaching, and that comes then to 0.7 cubic meters of air exchange. Here, this is from our formula sheet where it explains exactly the whole limitation. I'm leaving out the extract air rooms because they're really individual and they're normally not the dominant one in that calculation, but could be. Good. So here, 1 cubic meter per air, let us say that's what we have available. So now we come to the conditioning. So I want to explain now this formula here. So the available air volume, V, needs to be, is our limitation, what the heat recovery ventilation system can actually use. And then we want to apply it to the TFA. So we're coming to this 10 watts per square meter calculation. And that's now these two parts of the formula. Then here I explained already the air has a heat carrier, has a limited capacity, the thermal mass that that air has. And at 21 degrees, the heat capacity is 0.33 watt hours per cubic meter Kelvin. This figure is not really temperature dependent. Like if you go really in the back, it changes slightly, but we're always using the 0.33 watt hours per cubic meter Kelvin in our calculations. And that's that part of the formula. And if you wonder what that is, that's the magic formula. So that's the magic formula that we are teaching. We're having here the specific heat energy transport. We have our dimension multiplied by the performance of dimension, a correction factor, and climate data divided by the treated floor area. Dimension, point thermal bridges has no dimension. Linear thermal bridging is first dimension, meters. U values is second dimension, square meters. And volume is third dimension, cubic meters or cubic feet. And then we're having our performance of them. So that kills all energy calculations with this formula, just as a little insight. So now when we're coming now to the fresh air can be heated up to a maximum of 52 degrees Celsius, the 126 Fahrenheit. Why can we only heat it up to 52 degrees? You remember? Dust burn. Yeah. So otherwise the dust particles in the air starting burning, and we're getting this ugly oil heater smell that we're having in the winter when we're switching on our electrical oil heaters. Yeah, and then the heat temperature can cause dust carbonization. Yeah, that's that part. Then conditioning, the maximum possible thermal difference in this limited condition with heating is 32 Kelvin. That's 58, a thermal difference of 58 Kelvin. And that's now our thermal difference. That's that delta T here in the back of the formula. What is now the situation with cooling? Actually, I jumped over that quickly here. So this is now the calculation, 1 cubic meter of air by the capacity of air, the thermal mass of air, the storage capacity of air by the thermal difference divided by the TFA comes to this 10 watts per square meter, your 3.2 BTU per hour FT. Yeah, that's what comes in the standard. So on the heating side, happy days, no problem. But now we're coming to the cooling side. Cooling, what is now the limitation of cooling? Like the parameters are the same for heating, volume, and thermal difference. So when we look at our psychrometric chart, you may have seen that in your course, or maybe you're using it on an everyday basis. Maybe you've never seen it before, I don't know. Here we're having our temperature, 25 degrees, 77 Fahrenheit. When we're going now on the horizontal, we have our absolute moisture content. And when we're coming now to this point, we are reaching the 100% relative humidity. I'm going to the extreme, 25 degrees with 30% relative humidity. We don't want to go to a lower relative humidity. And then I'm going to the other extreme where we're reaching 100% relative humidity at 6 degrees. So it's the maximum capacity, that span between 6 degrees and 25 degrees is the maximum thermal difference we can use for cooling. Here's now our formula for that again. 25 minus 6 makes a thermal difference of 19 Kelvin. So the fresh air can be cooled to a minimum of 6 degrees, 4.2 Fahrenheit. And when we put that now into our formula, then we're having only 19 Kelvin thermal difference. What comes to 6 watts and not the 10 watts. So we only have 1.92 BTU per hour per FT square. Yeah, so lower temperature can cause dry air, condensation, or fog. I'm imagining that at this point, we have no condensation or fog formation at the outlets of my system. It's just something that we have, but maybe we have the risk of mold formation. So when do we have mold issues? At a relative humidity of 80% relative humidity. So that's the reason I'm moving now to 9 degrees. doing the whole thing again. And now we come to a capacity of 5 watts per square meter. When we're now looking at our passive house standard, we're seeing the 10 watts per square meter, use 3.2 BTU. That's here in our passive house standard. But the cooling has only a capacity of 5 watts per square meter and not the 10 watts. So if you're designing if you're designing with the load with 10 watts per square meter, we can't use the heat recovery ventilation system or the supply air as our cooling medium. So how could we achieve that? Obviously with a better building envelope, so improving the building envelope, better walls, grounds, roofs and grounds, better glazing, window frames and doors, higher construction costs for building envelopes. So that's the problem. In cold climate, the U value already be over designed for the cooling period. Yeah, so in cool temperatures, remember the thermal difference. Cold temperature, we're designing for the cold temperature and we're having already far higher thermal difference. So probably from in cool climates, the 5 watts per square meter is actually possible and no problem at all. Hot climates, that might be economical, but in hot climates or mild climates, we probably not design with 5 watts per square meter. Then a higher air volume, that's the other option, but this additional volume cannot come from the outside. The outer air has outer conditions and creates a higher conditioning load. Yeah, so we need recirculation. So for this presentation, I focus on air. Yeah, because I believe air is the right medium because we can switch it on and we can switch it off. Soon we're using a medium with a higher thermal mass, a higher capacity. The system is far slower and we will cause a really quick overheating of our systems. But I didn't want to go into much of that. That's what we're teaching in the course. But for today, I just focus on air. So bigger air volumes. What's the pros? Quick response, high cooling loads possible. Cooling is cheap or free. Cooling is only needed when the sun is shining, and the sun is shining and the PV on the roof could then create cheap or nearly free energy. Cons, lower safety during power shortage. So the problem, if you're designing with a higher load, power shortage normally happens at the highest thermal difference. Yeah, so coldest day or hottest day, or really a storm situation, but what that is normally as well, hot or cold. And then if there's a power shortage, we have a higher load, so the overheating is higher. This is the reason I highly recommend you to wire your PV systems in a way you can use them without the grid being connected to your house. Yeah, it's a safety feature. Yeah, making it safe in the summer. If ducted, if you have ducted situation, bigger pipes, then our 80 millimeter pipes, we need now 250 millimeter pipes. If the HR system is used, bigger gaps under doors for airflow, whistling. Otherwise, we create whistling. Yeah, a bigger volume of air for higher loads. The additional airflow cannot come from the outside because it would have the outside conditions. So we need to recirculate. Yeah, if we use the typical design approach of passive house, then we're having a transfer from one room to the other. We have supply rooms, we have extracts rooms, and that needs to move from one place to the other. So underneath our door, the gap needs to become bigger. So this would be then the way it looks, or maybe even bigger depending on the airflow. Or we need our vents in the walls, but now sound absorber is really, really needed. Other options is we are only having here our heat recovery ventilation duct coming and supplying air into the room. And now we're having in the room an air intake, having here a bigger duct and then here the air outtake. And in this duct, we are now conditioning the air. So our air conditioning happens only in that part. So where we have now a bigger volume and we're not creating pressure differences between the rooms and not creating pressure differences between inside and outside, because soon we pressurize a room, the pressure on our air tightness system is higher as well. So we create higher losses. So I'm a fan of air intake in the room and extract into the room, so we're not creating a pressure difference between the rooms, and that could be an option. The other option, my favorite one, is having your air supply via heat recovery ventilation system, having your conditioning system completely separated. So if you're now speaking about split systems, My approach is normally 3 split systems for cooling, and for heating would be the same. One in the biggest volume of the building, biggest air volume of the building, so that we can handle the biggest volume of the building. Then we want to use the staircase, top of the staircase, so we can get this trapped hot air that is rising and get it out. And then normally I say a third one in the master bedroom or in the home office, depending where you want to have it. So the biggest air volume upstairs in the staircase, and the master or office. That's where I normally recommend to put the split systems. If you're doing that, we're having 3 split systems to stay cool. A split system has normally about 2 kilowatt hours. If you take 3 split systems, we have now 6 kilowatt, and 6 kilowatt is about 8 horsepower. Yeah, so that maybe helps you with the understanding. One split system for 100 square meter with a maximum of 20 watts is now 1,000 feet with a maximum load of 6.4 BTU. So you see that's already really easy to design. If you have 3 split systems, we can have now a house with 300 square meter or with 3,000 square feet. Yeah, and that's the reason I normally say 3 splits for a normal home, easy peasy. Looking now at our standard, we're having here our load. The 10 watts is not possible if you're using our supply air, like that we're taking from the outdoor, then only 5 watts is possible. But if you're using split systems, you can even bring it up to 20 watts, not fulfilling passive house standard, the OR requirement. But if you're fulfilling the 15 kilowatt hours, you're still fine. Yeah, so then we have 20 watts available. And that's, I think, for especially the cooling side with cheap energy available and a suitable option. What systems are available? We're having in the moment this ugly roof thingies. We're having these ugly wall vents. We have ugly outlets here, and we're having these units here of fans. I think we can improve that. This looks maybe already a little bit better. If you come to commercial settings, we see that there are already ways of designing it far more beautiful. But maybe we should look a little bit to the car industry to get ideas of designing our ventilation systems. Okay, that was my presentation. Thank you, guys. Here, that's the dates of our next courses. Questions?
Very
Thank you,
nice
Daniel.
presentation, Daniel. Thank you very much.
Good.
We
Maybe
do
I'll
have
stop
a
sharing.
number of questions.
I'd probably stay in here. I could go back to the slides if it's slide related. Otherwise, I would like to stop sharing the screen so that we see each other. It's always
Sure.
nicer to see each other. So if there are slide related questions, maybe you want to do them first, and then.
Yeah, Daniel, we have 10 to 12 minutes to do questions before we break into that other part we spoke of last night. So have a glass of water for a second. Everyone else, roll back your shoulders, and Shannon's going to kick us off.
So we have a couple people coming up with questions, and the first one is from Rich. Rich, would you like to unmute and ask your question?
What dollar value are you using for your slides when you're referring to 3 cents?
It's actually coming from American dollars, but the difference is like, I think we could apply it for both because the richness of sun in Australia is so much higher again. So I think we are able to produce for true Australian cents in Australia.
Awesome. Thank you.
Thank you so much, Rich. And we have a question from Tom Phillips. Go ahead, Tom.
Oh, thank you. Great to see all these numbers crank through. I was wondering about just optimizing, number one, I guess, for all the different passive cooling measures to reduce the cooling load. That external shading and maybe even thermal mass and ceiling fans and so on to deal with things like radiant temperature and airspeed and other things. How much of a dent does that make? And number two is for future climate adaptation, the cooling loads are going to, maybe double in some areas.
But as well, our solar radiation doubles then. So the relation, when it gets hotter, we have more sun available. So that's the beauty of cooling. It's only needed when the sun is shining. So I'm not worried about cooling too much. Yes, obviously the first step is reduction. So there's a really easy way that we normally teach it: reduce, produce, store. First reduce, then produce, then store. The thing is, we have to think of it as well of reducing to an economical value. Yeah, like could we reduce it to 0? Yes, we can. We see it with Gilly Halls, like the student accommodation in Melbourne. They have no heating, no cooling at all. And that needs to be an economical approach because it's student accommodation. This needs to be economical. So we completely eliminated heating and cooling in that building. That was the economical outcome. I think if you're coming to the cooling, I think there is the one approach is getting rid of heating and cooling completely, or getting rid of cooling completely as an economical outcome, or a load area of about, like in hot climates, I probably have to distinguish in that one. Hot climates, the option could be completely getting rid of heating and cooling completely, or a load between 10 watts and 20 watts. Keep in mind, in Australia, for example, for apartment sizing, we normally use 130 watts per square meter. I'm speaking of 20 watts. That's super, super low, guys. Yeah, that's about 20 ice cubes melting in your kitchen. Yeah, from putting that into an option. Obviously, first thing is reduction. That's what Passive House is doing. Like the Passive House standard, Passive House approach is exactly about that. However, we have to think about the economics. Where is this economical optimum? Like we have local optimums and we have the global optimum. That's now science, and we need to be careful that we're not getting taken away with a local optimum and say, yeah, that is now the perfect. It might be far lower, it might be a little bit higher, whereas our global optimum from an economical perspective. Careful with thermal mass. Thermal mass is totally overrated. Thermal mass is only a storage capacity. It's not a thermal insulation capacity. Yeah, it's only how much energy can I store in thermal mass, and not really having an impact on the energy consumption. If you have the energy in the building, it's in the building. If it's now stored in the thermal mass, we still have to get it out of the thermal mass and cool it. The quantity of energy is the same. The only thing is what thermal mass is, it's helping you a little bit to the fluctuation in your house. But soon you're building passive, like I'm teaching, or like we are probably all teaching, then the thermal difference between hottest and coldest day is 20 degrees and 25 degrees. And a thermal mass needs a thermal difference, and a thermal difference is not existing in the internal room of a passive house. Yeah, so you need a massive thermal difference to have a really positive effect. If you have traditional housing where the temperature ranges between 5 degrees and 35 degrees, the thermal mass, you see the positive impact, but not soon you're building high quality buildings and high performing buildings. The thermal mass is a really limited parameter and is totally overrated in the general public.
I think you upset some people by that statement. I was looking at faces throughout the thermal mass, and I think a lot of us were like, "Oh no!" But I wanted to use thermal mass on a project. So thanks for the clarifier.
Yeah. So thermal mass, if you have it, you have it. If you don't, you don't. Yeah, it doesn't really make an impact on the performance of the building. Thermal mass can as well work against you if you have the typical Australian lifestyle where you have your Barbie, yeah, 35 degrees, 40 degrees day. You keep your fly screens closed, but you keep your glazing doors open, the typical approach in Australia. So all your heat from the outside comes now in, is now getting stored in your house. And now when finally all the guests are gone, you're closing your sliders, and now you're switching on your air conditioning, and now you pay for your thermal mass being actually in your house. Yeah, so a thermal mass heavy building is less forgiving than a lightweight structure.
Yeah, I agree that thermal mass is a double-edged sword, and
yes,
ideally, I'd like in our climate in Southern California, you get cooling breezes at night. And if you have controlled thermal mass, you can optimize that night ventilation with thermal mass, but then isolate it when you don't want it to cause a problem.
Yeah, and that's the problem. It's now the fault of the user. Yeah, we can design everything nice on paper, but then we have the user messing everything up again. Yeah, so the thermal mass, if you're really strict with it, it works well, but if you're not strict, then you're getting into trouble. On that note, John Burrell, he built a straw bale house that is already higher thermal mass than a normal thermal mass day. And he has a blind that he needs to manually control. I think he changed it to electric. And he forgot it one day. It took him 3 days to get the heat out again because he has no cooling system in there. So that's now when thermal mass works against you. So if you have it, you have it. If you don't, you don't. Thermal mass shouldn't be your decision maker for which building material or building approach you are using. If it's there, it's there. If it's not, it's not. Yeah. So like you shouldn't spend 3 times the amount of money to have now thermal mass in your building. Yeah.
Doesn't it depend also on the diurnal cycles?
On which cycle?
Diurnal temperature cycles, if you have contrast between daily temperatures and also night temperatures, like it is in the deserts, so that you can use that the differential to offset the difference. And
you can use your night purchasing with opening your windows, and we normally encourage to do that. The thing is, soon you do night purchasing, you can't do it via your heat recovery ventilation system. The volume is too small. It's again that limitation. You need to open your windows, and soon you open your windows. You have no ventilation. So in the case of bushfire, dust storms, all that stuff is coming now in your house. So you're having issues on that end. Obviously, you can use it. We have the Fremantle doctor in Perth that comes always nicely in the afternoon. That is cooling down buildings. Like Fremantle doctor is wind. Maybe need to explain that. There's not a doctor coming to every house every day. But the Fremantle doctor helps to cool down the houses with that breeze coming. But it's now a natural force that we can't rely on. Yeah,
Thank you, Daniel. Thank you so
sense?
much.
Okay.
We have one more question before we ask you to show us your inspirational source, and that's from Reed Rollins. Reed, did you get your question answered, or do you still have half of it left? I know you and Kevin were going back and forth on the chat a little bit.
Keep in mind, I'm down to 2% battery power, so I may drop any moment. But I always thought the cooling was more costly than the heating.
Not in a sustainable energy industry. So we are on renewable side, it's far cheaper.
But how about if you're a climate zone? If you're in Yuma, Arizona, that is just always hot, your cooling loads have to be higher.
Not if you're designing it like Passive House, what allows you a specific amount of energy to condition your place in your location. Yeah, like Passive House is not telling you to use this builder. Passive House is telling you you have to get that performance with your builder. Make sense?
And correct me if I'm wrong, Daniel, the reason that you are making this statement is because when the sun is shining, energy is free. You're assuming that we're using solar technology. And that's why it's cheaper, Reed, I believe.
Okay.
Yeah.
All right. That makes a little more sense.
Soon we're coming to high humid places where we have maybe a strong cloud cover. We have to speak about dehumidification. That's now a different topic because you may have a high dehumidification load and not the necessary, and you probably need to size your system of significantly bigger to get as well your dehumidification happening. But that's a different topic. It's a different size. Could be another presentation.
Agreed.
Daniel, I'm glad you said that, because that was my question, was what happens when it's overcast?
Yeah, then it's less hot, but more humid. And now do we use ERV or HRV and like energy recovery or heat recovery? It's a completely different kettle of fish to discuss that. That's the reason I stayed on heat, like on our sensible heat and not the latent heat.
Right, latent heat. Now, Daniel, would you be willing to reshare your screen with us and share with us the person who has inspired you and brought you to the place where you are today, a mentor?
Actually, I have been thinking about it, and like I haven't prepared a slide for that. I think it would be unfair if I would share one mentor, because There's so mentors that impact me, from Bill Gross, Bill Gates, Tony Robbins, Wolfgang Feist, Dalai Lama, Arnold Schwarzenegger, and so many more. I think it would be unfair to just mention one. I think I am who I am because of leaning and standing on shoulders of giants that I've been learning from. But I would like to thank somebody else. I want to thank my team, because the only way that I'm able to produce such beautiful slides and this quality and be out there and making a difference is that amazing team that I'm having with Smart Plus Academy. And it's the best team I've ever worked with in my whole life. It's, yeah, like we're all really having the same values. We're all believing in the mission. Thank you for your trust. Thank you for believing in the mission of Smart Plus Academy. Yeah, we are here to inspire and lead with passion and love for now, for the future generations, and for our planet. That's us, guys. We do it.
Love that so much, Daniel. And your picture of your coworkers and teammates from the beginning is really sweet. You all look like peas in a pod.
Yeah.
Well, we're going to pass it over to Zach to end out our first hour before we kick off the after hour.
Thank you. And Daniel, this is amazing. Thank you so much for this presentation tonight. Really fantastic. So everything that we do at the Accelerator comes thanks to support from our sponsors. None of the work that we would do would happen without them. So I want to say thank you to these fine organizations and encourage everyone to include them in your projects when you have the opportunity to do so. So our founding sponsors are 475 High Performance Building Supply, Baxtingwe Architects, Mitsubishi Electric Train HVAC US, Partel, Glavel Foam Glass Gravel, Minutair All-in-One HVAC and Dehumidification, RDH Building Science, Rockwool North America, Stocorp, and Zola Windows. Our champion sponsor is SIGA, and our stakeholder partner is NYSERDA. Our patron sponsors are AeroBarrier, Inotech Windows and Doors, BR+A Consulting Engineers, US Engineered Wood T-Stud, and Brennan Air Tightness and Insulation. We have a great podcast episode live now. It's an interview with Petra Werner from Germany about the first passive house hospital. And this is an interview conducted by guest co-hosts to the podcast, Ilka Cassidy and Mary James. Really fantastic episode. Please check it out. And speaking of podcast episodes, you can also go back to episode 20 and catch Matthew Cutler Welsh's conversation with Daniel, which is also fantastic. Tomorrow we have Talina Edwards. So this is a down under week for us at Passive House Accelerator. Tomorrow we have Talina Edwards presenting about the Australian project Owl Woods Passive House. This is an award-winning project and super well organized and fascinating presentation. We just went through it with her yesterday. So please join us and catch that tomorrow. Next week, we're joined by none other than Gary Klein of Gary Klein Associates to talk about reducing the time to tap. And so he'll be talking all about hot water and efficient domestic hot water delivery. And then Global Passive House Happy Hour next week will feature Jeremy Huerta, Paul Warwick, Scott Kennedy, and Luke Hahn presenting about the Peaks project in Vancouver. And so we're going to get a perspective from the architects as well as the builders on this cool multifamily building in Vancouver, BC. So I think that's it for me. Thanks.